Given any integers, we can add, subtract, multiply, and sometimes divide them. So we can usually solve linear equations like ax plus b equal to c. Since we can add, subtract, multiply, and sometimes divide integers mod n, this means we can usually solve linear congruences of the form ax plus b congruent to c mod n. For example, let's try to solve 3x plus 5 congruent to 2 mod 11. Now, if this were a linear equation, we'd subtract 5, then divide by 3. Now, since this is a congruence, we could subtract 5, but we won't. Remember, it's easier to add and to multiply. And for any modulus n, n is congruent to 0 mod n. So we note that if we add the modulus, we don't really change what is congruent to. So negative 5 plus 11 is congruent to negative 5 plus 0. And so that says 6 is congruent to negative 5. And that means that adding 6 is the same as subtracting 5. And so we'll add. And since 11 is congruent to 0 mod 11, we can drop it out. Now, in a linear equation, our next step would be to divide by 3, but we can't divide mod n. Instead, we need to find the inverse. So to find the inverse, we'll apply the extended Euclidean algorithm to find the greatest common divisor of 3 and the modulus, and so we get, which tells us the greatest common divisor is 1, so an inverse exists. So we'll rewrite our quotient in product and sum form, and then solve for the remainders. And so we can find 1 as a linear combination of 3 and 11. And the inverse of 3 will be the coefficient of 3 in the linear combination giving 1. So our multiplicative inverse is 4, so if we multiply both sides by 4, we get, and remember, working mod n means never having to deal with any number larger than n, so we can reduce 32 down to 10, which gives us our solution. Note that our solution is expressed in the form x congruent to 10 mod 11, and that means that it's any x value that's congruent to 10 mod 11. Sometimes we're interested in the least positive x, which would just be x equals 10, but remember this does include a number of solutions. So let's try to solve, if possible, 8x plus 3 congruent to 7 mod 12, and if it's not possible, we should be able to explain why. So again, to solve this, we'd subtract 3, and in this case, we'll just subtract 3 because we can do that subtraction over on the right-hand side. Next, we'd need the inverse of 8. But since the greatest common divisor of 8 and 12 is not 1, no inverse exists, so we can't solve this congruence. Or can we? Remember, a problem exists whether or not you know how to solve it. And in this particular case, the thing to note is that we can't solve the problem by multiplying by the inverse of 8, but this doesn't mean we can't solve the problem. It only means we can't solve it using one method. There might be a different method of solution, or the problem might actually be unsolvable. So remember, trial and error is always a possibility, and since we're working mod 12, if x is a solution, it must be congruent to one of. So we could try each one and see if they solve the congruence. And so we find that if x is 0, 8 times 0 plus 3 is 3, which is not congruent to 7. 8 times 1 plus 3 is 11, which is not congruent to 7. 8 times 2 plus 3 is 19, but 19 is congruent to 7 mod 12, so x congruent to 2 is a solution. And a useful idea in life: don't stop just because you've found a solution. In fact, if we keep going, we find that 8 times 5 plus 3 is 43, which is also congruent to 7. 8 times 8 plus 3 is 67, also congruent to 7. And 8 times 11 plus 3 is 91, also congruent to 7. So we actually have 4 solutions, any value x congruent to 2, 5, 8, or 11. Since 8x plus 3 congruent to 7 mod 12 has 4 solutions, it's clear that a linear congruence could have more than one solution. We only found one solution to 3x plus 5 congruent to 2 mod 11, and so the natural question to ask is, could there be more? And we could check by seeing if x equals 0, 1, 2, 3, all the way up to 10 is a solution, and we find that there is in fact only one solution. We can take a look at a third one, 3x plus 2 congruent to 6 mod 15. As before, the greatest common divisor of 3 and 15 is not equal to 1, so we can't solve this using the multiplicative inverse. But we can always use trial and error, and we find and we see that there is no solution. And this leads to a somewhat complex situation. A linear congruence can have one solution, multiple solutions, or no solutions. Now, if a congruence has no solutions, it would be nice to know before we try to solve it. And if it has multiple solutions, we should know that as well so we can find all of them. But how can we decide? We'll take a look at that next.